Welcome back everyone. Today's topic is about vaccination, and in this one I will talk about part 1 of it, types, side effects and the composition of vaccines. Vaccination is the act of introducing a vaccine into the body to produce protection from specific disease, whereas immunization is a process by which a person becomes protected against a disease through vaccination. There are many types of vaccines, which is categorized by the antigen used in their preparation. Their formulation affects how they are used, how they are stored, and how they are administered. Vaccine may be monovalent or polyvalent. A monovalent vaccine contains a single strain of single antigen, whereas a polyvalent vaccine contains two or more strains or serotypes of the same antigen. For example, measles vaccine is a single antigen vaccine, and OPV vaccine is a polyvalent vaccine because it contains 3 antigens. Some of the antigens above can be combined in a single injection that can be prevent different diseases or that protect against multiple strains of infectious agents causing the same disease. For example, combination vaccine DPT combining diphtheria, pertussis, and tetanus antigens, or a pentavalent vaccine which combines DPT plus Haemophilus influenza and hepatitis B. Combination vaccine can be useful to overcome logistic constraints of multiple injections and accommodate for a children's fear of needles and pain. When we see types of vaccine based on the antigen used in their preparation, the first one is live attenuated vaccine. Live attenuated vaccine, an example is from bacterial tuberculosis, and from viral oral polio vaccine, measles, rotavirus, and yellow fever. Live attenuated vaccines are derived from disease-causing pathogens that have been weakened under laboratory. They will grow in a vaccinated individual, but because they are weak, they will cause no or very mild disease, except in immunosuppressed people. Live attenuated vaccines stimulate an excellent immune response that is nearly as good as compared to an infection with the wild-type pathogen. And the live microorganisms provide continual antigen stimulation, giving sufficient time for memory cell production. In the case of viruses or intracellular microorganisms, where cell-mediated immunity is usually desired, attenuated pathogens are capable of replicating within the host cells. Regarding safety and stability of live attenuated vaccine, attenuated pathogens have the very rare potential to revert to a pathogenic form and cause disease in vaccines or their contacts. Examples for this are the very rare serious adverse events of vaccine-associated paralytic poliomyelitis and vaccine-derived poliovirus, which is associated with oral polio vaccine. Sustained infections, for example, tuberculosis vaccination can result in local lymphadenitis or dissemination of infection. The other side effects or safety concerns of live attenuated vaccines, if the vaccine is grown in a contaminated tissue culture, it can be contaminated by either viruses. As a precautions, live attenuated vaccine tend not to be administered during pregnancy. However, the actual potential for fetal damage remains theoretical. Many live attenuated vaccine requires strict attention to the cold chain for the vaccine to be active, and they are subject to failure when this is not adhered. Inactivated whole vaccine or killed antigen. From this group, from bacterial whole cell pertussis vaccine and from viral inactivated poliovirus or IPVs, an example of inactivated whole vaccine, which are killed antigens. Inactivated vaccines are made from microorganisms that have been killed through physical or chemical process. When we see the immune response to inactivated whole vaccine, inactivated whole cell vaccine may not always induce an immune response and the response may not be long-lived. Several doses of inactivated whole cell vaccine might be required to evoke a sufficient immune response. Regarding safety and stability of the inactivated whole vaccine, inactivated whole cell vaccine have no risk of inducing the disease that they are given against, as they do not contain live components, and they are considered more stable than live attenuated vaccine in the case of cold chain failure. The other is subunit vaccine. Regarding the immune response to subunit vaccines, like inactivated whole cell vaccine, they do not contain live components of the pathogen. They differ from inactivated whole cell vaccine by containing only the antigenic parts of the pathogen, that are necessary to elicit a protective immune response. Often, a response can be elicited, but there is no guarantee that immunological memory will be formed in the correct manner. When we see the safety and stability of subunit vaccines, like inactivated vaccines, subunit vaccines do not contain live components and they are considered as very safe. Three types of subunit vaccines are there: protein-based, polysaccharide, and the conjugate subunit vaccines. When we see protein-based subunit vaccines present as an antigen to the immune system without viral particles using specific isolated protein of the pathogen. A weakness of this technique is that isolated proteins, if denatured, may bind to different antibodies than the protein of the pathogen. Commonly used protein-based subunit vaccines are the following: a cellular pertussis vaccine. A cellular pertussis vaccine contains inactivated pertussis toxin, which is a protein, and it might contain one or more other bacterial components. And the pertussis toxin is detoxified either by treatment with a chemical or by using molecular genetic techniques. The other is hepatitis B vaccine. This is composed of hepatitis B virus surface antigen, a protein produced by hepatitis B virus. And earlier vaccine products were produced using purified plasma of infected individuals. This production method has been replaced by recombinant technology that can produce hepatitis B surface antigen without requiring human plasma, increasing the safety of the vaccine by excluding the risk from potential contamination of human plasma. The second part of subunit vaccine is a polysaccharide vaccine. Some bacteria, when infecting humans, are often protected by a polysaccharide capsule that helps the organism evade the human defense systems. Polysaccharide vaccines create a response against the molecules in the pathogen's capsule. These molecules are small and often not very immunogenic. As a consequence, they tend to not be effective in infants and young children, and they might induce only short-term immunity, slow immune response, slow rise of antibody levels, and no immune memory. Examples of polysaccharide vaccines include meningococcal disease caused by Neisseria meningitis groups A, C, W1, D35, and Y, as well as pneumococcal disease. The other subunit vaccine is a conjugate subunit vaccine. Conjugate subunit vaccine also creates a response against the molecules in the pathogen's capsule. In comparison to plain polysaccharide vaccines, they benefit from a technology that binds the polysaccharide to a carrier protein that can induce a long-term protective response even in infants. Conjugate subunit vaccines can therefore prevent common bacterial infections for which plain polysaccharide vaccines are either ineffective in those most at risk, for example infants, or provide only short-term protection for the rest. The advent of conjugate subunit vaccines herald a new age of immunization against diseases caused by encapsulated organisms such as meningococcus, Haemophilus influenza type B, and pneumococcus. The fourth one is Toxoid vaccine. Toxoid vaccines are based on the toxins produced by certain bacteria, such as tetanus or diphtheria. The protein-based toxin is rendered harmless, and they are used as antigen in the vaccine to elicit immunity. To increase the immune response, the toxin is adsorbed to aluminum or calcium salts, which serve as adjuvant. Regarding safety and stability of the toxoid vaccines are safe because they cannot cause the disease they prevent, and there is no possibility of reversion to virulency. The vaccine antigens are not actively multiplying, and they do not spread to unimmunized individuals. They are stable, and as they are less susceptible to change in temperature, humidity, and light, this is also good in the case of problem in cold chain. The second issue in my today's topic is about components of a vaccine. Vaccines include a variety of ingredients including antigens, stabilizers, adjuvants, antibiotics, and preservatives. They might also contain residual byproducts from the production process. Knowing precisely what is each in vaccines can be helpful when investigating adverse events following immunization and for choosing alternative products for those who have allergies or have had an adverse event known or suspected to be related to vaccine component. From the component of vaccine, the first one is what I have discussed above about the antigens. Antigens are the components derived from the structure of disease-causing organisms, which are recognized as foreign by the immune system and triggers a protective immune response to the vaccine. The other is about stabilizers. Stabilizers are used to help the vaccine maintain its effectiveness during storage. Vaccine stability is essential, particularly where the cold chain is unreliable. Instability can cause loss of antigenicity and decreased infectivity of live attenuated vaccine. Factors affecting stability are temperature and acidity or alkalinity of the vaccine. Bacterial vaccines can become unstable due to hydrolysis and aggregation of protein and carbohydrate molecules. Stabilizing agents include magnesium chloride, magnesium sulfate for measles, and magnesium chloride for OPV, lactose, sorbitol, and sorbitol gelatin. The other is about adjuvants. Adjuvants are added to vaccines to stimulate the production of antibodies against the vaccine to make it more effective, more often in inactivated or killed vaccine. Chemically, adjuvants are highly heterogeneous group of compounds with only one thing in common, which is their ability to enhance the immune response. They are highly variable in terms of how they affect the immune system and how serious their adverse reactions are due to the resulting hyperactivation of the immune system. The other is antibiotics. Antibiotics in trace amounts are used during the manufacturing phase to prevent bacterial contamination of the tissue culture cells in which the viruses are grown. Usually, only trace amounts appear in the vaccines. For example, MMR vaccine and IPV each contain less than 25 micrograms of neomycin per dose. Persons who are known to be allergic to neomycin should be closely observed after vaccination so that any allergic reaction can be treated at once. The other is preservatives. Preservatives are added to multi-dose vaccines to prevent bacterial and fungal growth. They include a variety of substances, for example, thiomersal, formaldehyde, or phenol derivatives. This is all about part 1 of vaccination. Thank you for watching.